begin the event formally, I would like to call our chairperson of IEEE Photonic Society Kolkata chapter, Dr. Prof. to deliver the welcome address.
Good afternoon, everyone. It is my great pleasure to welcome you all to this special seminar organized in celebration of the International Day of Light. This day, observed annually on May 16th, is a global initiative that highlights the central role of light-based science, culture, education, and sustainable development. From the marvels of optical technologies to the beauty of natural sunlight that sustains life on Earth, light touches every aspect of our existence. Today's seminar is organized to reflect on the importance of light-based technologies and to explore their impact on communication. We are honored to have with us Professor Abhirup and Dr. who will share valuable insights into how light is transforming our world and shaping the future. I extend my sincere gratitude to our organizing team and everyone who participated in making this event possible. So once again, a warm welcome to each of you. Let us celebrate the power of light and the power of knowledge together. Now I request Professor Abhirup to come on to the dais to deliver this lecture, and let me introduce first Professor Barman. Abhirup received the bachelor's degree BTech in Electronics and Communication Engineering from the Institute of Radiophysics and Electronics, University of Calcutta in 1991, and thereafter master degree MTech in Electrical Engineering from IIT Kanpur and PhD from Institute of Radiophysics and Electronics, University of Calcutta. In between, he worked with years in Indian engineering service in the area of satellite communication, digital terrestrial transmission, etc. Then he joined as a faculty in the Department of Radiophysics and Electronics. Since 2014, he is a professor in this department. In 2007 and 2009, he worked as a distinct researcher at the CNIT Networks National Laboratory, PISA. In 2010 to 11, he worked as a researcher in Albert University, Denmark, with the Department of Electronic Systems. In 2015, he worked as a visiting researcher in Limerick University, Ireland, Department of Computer Science and Engineering, under Erasmus Mundus European Union Scholarship. He has more than 85 publications in international journals and international conferences, and supervised many PhDs. He was a principal investigator to join Indo-Italy bilateral project of BSD and high-value project cognitive radio communication of MIT-Q1. His present active area of research is microwave photonics, PLC, signal processing in communications, including radar signal processing. I request now Professor Barman to start this lecture.
Good afternoon, everyone. Thankful to the organizer for inviting me to giving a lecture on the International Day of Light, and I'm very proud of that. Okay, so I choose the topic deliberately, visible light communication. In our room, you see a lot of LEDs are there. It is possible to communicate with such kind of LEDs inside a room, and a lot of other applications are there, which we recently call optical IoT. You know about the other IoTs, but you didn't know what is optical IoT. So I will give some applications of the optical IoT first, and then I will go into the subjects. But since it is a popular lecture, I purposefully divide off using mathematics. A lot of mathematics are there inside, but those I try to simplify just to give you the idea that how the things works. So it is basically a kind of popular lecture. So to start with, indoor visible light communications with white LEDs. You see all the lights are white. So it's a very recent, what I should say, development because of the invention of the green LED, which was earlier energy drooping and could not be efficient. And for that, people used to use the phosphorus-based white LED. But nowadays, the things have been different that I will talk about. So let's enter into the subjects. The first optical wireless communication, as we know that earlier civilizations, then we use fire and smoke to detect the signal from a distance. And the first example of the free space optical wireless communications was mooted by Alexander Graham Bell in 1880. Okay, so almost 19 years before, I think the Marconi has first made the experiments in wireless communication. So what he did, he actually transported the voice signal modulated on the sunlight and transmitted it. So it is basically a optical communication because sunlight was used, and selenium cell vibrates according to the audio signals or sound signals, and that sound signal is and the light is modulated by the selenium cells. Okay, so that was the main purpose. The first, very primitive. Nowadays, selenium cells has been used for other many purposes. I'm not going into detail of that. So let's first go into a little bit of the classification of optical wireless communication, where it is. You see the almost every sphere of light it is currently being used. Okay. So you see the ultra long range FSO. It is segmented into different classes: ultra long range, medium range, short range, and like that. So in the case of ultra long range FSO, you can see the communication between the two satellites using the laser beam. Okay, so it is a laser communication. LED cannot propagate such a long distance. And also you have a communications. Can I use this? Okay. And also you see that in the ground there is earth stations, and that can be connected to the satellites using the laser beam. And ISRO Ahmedabad is already doing this. And not only that, with the aeroplane also can be connected to the satellite using the optical beams. Okay, so. Sorry. Mouse yeah. Sorry. No. Yeah. So such kind of communications take place, ultra long range free space optical communications, and then you can also have this long range FSO where you can put a link between the top of the buildings. You see the red lines, they are the laser beam is propagating from one beam to one place to another. In our earlier student days, we have a communication link between this building and the CS building. So it is a very short range, but long range kind of communication is possible. And this is very low cost compared to the optical fiber. That is why people sometimes prefer this. The medium range FSO, you have the lighthouse where you can communicate between the ships. Okay, you see the communication between ships, as well as you can communicate the scuba diver went inside the water. So you can see the scuba diver, it is a little bit of hazy in the down inside the water. That can be communicated with the ship, as well as it can be different submarines can be communicated. But it cannot be a long range because, as you know, the optical frequency has a higher loss in water. So that we cannot use a long distance for that. Then come into very interesting thing, another applications called the V2X, that is the vehicle to anything, X means anything, correct? Here we have used the vehicle to the infrastructure. You see there are a lot of lampposts, the cars are moving, there are a lot of lampposts. So from lampposts, they are connecting with the with the lights of the car. Okay, so you can see this. They are being connected like that. So how it actually works, that has been explained in the diagram below. And if you see that, there are three light sources are coming in and falling on the infrastructure. In the infrastructure, what is there? It is called the optical camera control. OCC means optical camera control, where you have a CMOS image sensor. Basically, it is a camera image sensing. So those things are there here, and the light which falls on the lens, you see there is a white lens. Can you see this where the light falls? And there it is focused on the image sensor. So you see that most of the things in the daytime, the sunlight will be there, and sunlight is really these signals are being contaminated with sunlight as a noise. So how intelligently they have removed the interference of the sunlight. So you see the sunlight has been focused to a different point in the image sensors, and the red light and the green light which is coming from, they are being focused at a different points. But you cannot have a very high bit rate because these cameras are not an ordinary camera. If you see the ordinary camera, you have 30 frames per second is the frame change. But this is a very fast camera, which at least to have 200 frames per second, the frame changing rate. And because why we have made it such a high speed? Because the bit rate or the image rate, which is falling on the pixels, they should have at least half of the frame rate to satisfy the Nyquist rate. Okay, so that means you have bits per second per pixel. Rate is of the order of 100 that you can get utilizing such architecture. And not only that, you have to also ensure that the image size, the image which is formed on the image sensor, that size should be more than the pixel size. Otherwise, you cannot detect that. So if you follow these guidelines, you can have an image. And using the image signal processing, you can simply extract out the data. So this is what is called the OCC, and it is coming up tremendously in different sectors. If you see, I will come to that. It is another important application. You see that this is called the indoor position by the optical camera control. It is what it is done. If you go to the shop floor or on some shopping center, it's huge. If you go abroad, you cannot find where is the exit gate. It's such a huge. So it is very difficult to also find the objects where it is placed. So you can easily find the object because inside the room or inside this building, the GPS doesn't work. It is very faint. Okay. So what they do you see these LEDs are there in the top of the things, and each LED has an identification number. So this mobile, the person who is carrying this mobile, he first connected with the LED and get the unique identification code first. So he first connects with the LED, and then you have a smart app there, so it knows its positions and the object he wants to go there. You see the path, so it will show you that if you go to this path, you can end up in the near to the top. So it is basically a positioning controlled by the optical camera control. So so it will show you the path, and if you follow those path, you can end up with that objects to arrive. And this is the ultra short range of communication. This is another important application which is coming up in a very big way. You see the most of the sensors which are there is based on LEDs. It is a wearable LEDs. Because the advantage of this that there is no RF interference. Most of the hospitals everywhere, a lot of RF equipments work there. So if you use the RF sensors, it actually interfere with that, and they don't allow it. So if you instead of that, if you can use the wearable LEDs, and nowadays you have bio LEDs, a lot of LEDs are coming up in the market. So if you use the LEDs that can directly connect it to a robot, you see that, and the robot is having that image sensor, the camera control. So it gets that image, decipher that image processing algorithm is going on, and gets that image. So ECG is nothing but a form of image, so it can get out the parts and other parameters from that. And not only that, you can also have a very ultra short range communication between the two chips. You see there are a lot of chips are there. So you can see the red line is a connection between the two chips. Not only that, if you have a chip structure like that, you can have the connections like a ring network. Okay, so even nowadays, if you go to data centers, you will find all the interconnects are all by the optical connects. So this is what is a very short range communications. So how it actually works? This is much more technical. The source data is entering, it is encoded, and then there is a modulator with the optical source. This optical source contains either laser or LEDs. Okay, in this block in the down, and that is being input data is being modulated by the lights, and that is being amplified with optical amplifier, and then it is being transmitted by the optical beamformer. Okay, so it is transmitted, and in the receiver, it is a very, very simplified and the cost-effective receiver. We call it a direct detection receiver, and which is simply detects the light by using a photodetector. And then we have after photodetector, it becomes electrical, from optical to electrical. And then from electrical, it's actually low noise amplifier. And there's a gain control in the low noise amplifier. Then there's a low pass filter, and it demodulates the data and gets the received information. So this is more or less whatever we show in the earlier examples. In this way, the optical transmitter and receiver works. But this is the direct detection receiver. It is not a sophisticated one, very cheap, and people like to work with this. But more sophisticated instruments are like this. It is called coherent detection receiver, where you see that I have shown only the receiver section, where the input of transmitted optical beam has arrived, is sent, and it is passing through the atmospheric turbulence. Because when I show you that there is a link between the two wavelengths, maybe fog may be there, so the waveform get distorted. Or even if you connect a earth station with the satellites, it travels through the air and the beam gets deformed. So you see the beam gets deformed. So at the beginning, before the collecting lens, you have a kind of MEM structure you can produce, where actually this beam, the distorted beam will make again the parallel beam. So those MEM structures, this is also a very good topic of your PhDs. The MEMS you can build up the mirror, you can either mirror or some optical array of mirrors you can arrange and can set the beam right. And that falls on the collecting lens, and then it actually combines with a local oscillator. Local oscillator either having the frequency of the local oscillator is chosen in such a way that the frequency of the incoming optical beam and the local oscillator difference is the IF. And that being detected by the photodetector here. And then this IF filter, because I said that the difference between these two is IF. So it is IF and then envelope detector, and we get the signal to noise ratio at the output. The most important thing, because why we choose such kind of coherent beam detection, it is very, very highly sensitive. And not only that, because of the multiplication with the local oscillator, the beam is quite powerful there at the receiving end of the detector. And not only that, the F filter, which is at the much lower frequency of the order of megahertz, you can build up a amplifier system which is having a very high gain, because high gain amplifier design is much more simplified when you have a lower frequency. If you have a very high frequency, it's very difficult to actually design an amplifier. And that is the reason behind it, that the difference between the two input signals, optical signals, and the local oscillator is also a laser source. So this difference is the IF, and the IF is being filtered out and being amplified, and you get out the signal after demodulations. Fine. So now comes to the topic, the visible light communications. So first I will tell you the need for visible light communication, why people are so much of interested to use it. And then I will use the white LEDs. Why LEDs are used for visible light communication, that I will tell you. The two technological challenge I will just emphasize here. One is called the light modulation, which is the two modulation techniques are there. Primitive on-off key, pulse width modulation. These are all primitive kind of modulations. But nowadays, a new technique called CSK. It is a new, very, very new technique. I will try to explain you in a very layman language, called the color shifting. It's a new kind of modulation things are coming out. And OFDM is quite mature. It is called optical OFDM. That is also, we have worked on it on this two modulation technique that I will explain. And I will tell you a little bit about the challenges of OFDM and how we can get the solution. That also we have devised the solutions and some few research work we have done. Time will not be there to permit me to do to narrate all the research work we have done here. And finally, conclusions. So let's see, the first start with the visible light communication. You see the picture here, you see it is taken from the Korean University. They have already implemented the visible light communications there. Inside the seminar room, you see the lights are falling with the transmitted bits. You see the bit stream, it is showing in the lights. So that is being directly connected to the monitor, and it is so all the internet connections being connected to the monitor. So there is no one is presenting here. All are listening. All are viewing this monitor, and it is directly connected with the internets. So and those internets connection being done by the help of this light source in the room light. So that is a beautiful beauty of this. So this is one example, and another example inside your room also. You have a table lamp with full of LEDs, so you can have a communication. You have a lighting as well as a communication. Okay, so these things are possible. Simultaneous lighting and communication. That is why it is so attractive, because light energy is already you are burning up the energy. So along with that, if you have a communication, it is a benefit. Okay, that is the main idea. And why it is being carried out? There is an exponential demand of data rate. The first generation, second generation mobile, third, fourth, fifth, and sixth is coming up already here, and then sixth will be coming up. And the microwave frequencies below 6 gigahertz is almost finished. And that is why people are looking for new frequencies where to work with, because without frequency, we cannot have the communications. So there are two domains where you can work with a new frequency. One is called the millimeter wave communications, where the frequencies are plenty. And the second one is the optical wireless, where the frequencies are plenty. So these are the two things. The spectrum is vacant in the millimeter wave as well as in the optical domain. Okay, so these two one can exploit in a bigger way. So it is not coming in a very simple way. In this IEEE Communication Magazine in 2014, you see I have put the name of Harold Haas, whom I met in one of the invited lectures at San Francisco, and he told me a lot of stories about that. And they have rooted out that in the cellular architecture, visible light communication should enter. And because there is a license is already free there, you need not to pay anything for using the visible light communications. So they argued that visible light communication should be a part of the 5G communication, because 5G communication, when it will be used, the augmented reality, virtual reality, and digital twin, 3D printing, so many things will come up, and you need a lot of data in the real time. Who will supply such a huge kind of data? It is impossible to supply it with a simple RF communications. So new avenues has to be ventured, and that is why this visible light communication has come out. So this is one example of this. The second one also have to tell another IEEE Communication Magazine. They have identified 5 disruptive technology, and those 5 disruptive technology, it is visible light communication is one of them. Okay, so I'm taking what is disruptive. Because disruptive means there will be a component change as well as architectural change in the networking. That is why it is called a totally complete change from the normal current cellular communications. So that is why they call it a disruptive. So what are those 5 disruptive technology? I've narrated it down. It will be coming in a heavy way, a big way in 5G communications. One is a massive MIMO communications. The second one is a millimeter wave communications. And the third one is device-to-device communications. Device-to-device means everybody is having the mobile. So I have my mobile, I can connect with him. His mobile can be connected to that. Like that, it will go to the base stations, not directly to the base stations. This is what is called the device-to-device communications. And then we have a machine-to-machine communications, because a lot of shop floors are there, which wants to connect their machines, their shop floors globally, so that they can control their productions. So that is why the machine-to-machine communication is coming in a big way. And Internet of Things is already being exploited in most of the applications. And the final, you see the visible light communication. So among the 5 disruptive technology, visible light communication has taken its place. So you see the wireless communication frequencies, as I said, in the orange, you see up to 6 gigahertz completely failed. No chance of putting up a very high data rate communication systems. Then you have a millimeter wave of 30 gigahertz where people are exploring in a 5G, but it has a problem that if somebody goes, the millimeter wave totally obstruct the signals, and it simply so they have a different kind of architecture. That is why it is called the disruptive technology. So completely different kind of architecture is coming. So another one is the visible light communications. You see, it works between 380 nanometer to 780 nanometer. So this is the visible light communication range. And if you go to the millimeter wave, that is called the new radio, 5G new radio, which works on 26 gigahertz, 28, 60, and 78 gigahertz, where the atmospheric windows are available, so you can communicate with that. Without atmospheric window, you cannot communicate. So in this frequency range, there are atmospheric windows, and you can communicate. Okay. So let's see what is the advantage. It is a large bandwidth. It is optical signal. You have a almost as I showed that it is between 380 to 780 nanometer. That means it is of 400 nanometers. And 1 nanometer, if you calculate, it is of the order of 120 gigahertz. So 120 gigahertz multiplied by 40, so much of bandwidth is available in the optical domain. So one can exploit that. So that is by large bandwidth. And then the license-free operation. If you want to communicate with this thing, government will not charge you anything for communication in this frequency. So this is license-free. People are attracted. And in recent Samsung mobile, if you see the Samsung mobile, I forgot the number. They have connected the photograph on the Samsung mobile. Beautiful thing. So they already assume that the people are going to exploit the LED communication with the mobile. So they put a photo picture on the Samsung mobile. And no interference with the RF-based system. There is another important advantage. If you go to the hospitals and the aeroplanes, where a lot of RF equipments are being used there, so this kind of communication will not interfere with the RF equipments. A very big advantage. Free from health hazards. Of course, you should maintain the safety regulations. So there is no chance of getting eye contaminated or skin because the LED powers is not so much. That is the biggest advantage. Okay, and no intercell interference. I'm not going to cellular communication, so interference is also very less. So you see this picture inside the room, as you have the LED lights in the top, and you have the connection of the connection with the mobile phone as well as in the laptop, like that. And here you have the transmitter transmitting is LED, and the detector you can use either PN photodiode or simply avalanche photodiode, or currently people are heavily exploring the CMOS imaging sensors as signal receivers, because most of the mobile you are having a camera, so you can easily capture those images. Okay, so fixing the light fixtures in the setting in the room, personal wireless networks can be established. As I show here, a lot of light LED fixtures, LED arrays are there in the top, and you see the person is moving. So mobility you can provide. These cells are very small, of the order of 5 to 10 square meters only 5 to 10 square meters. So if you move around this lights will automatically take care of above you. So a lot of handover is there. That issues I'm not discussing. Those are mostly technicals. So you see that the LED also very luminous efficiencies of the order of 200 lumen per watt. That is the biggest compared to normal earlier days incandescent lamps. Only 51 lumen per watt, almost 4 times the powerful the LED lamps. And nowadays, if you go with the surgery, you will see a big lighting system. Almost 50 LEDs are being connected, and such a huge light is being formed. This is possible because of the huge luminous efficiency of the LEDs. Okay, so I have made a comparison. You see that 200 lumen per watt. Not only that, its lifespan is of more than 50,000 hours compared to other 10,000 and 1,000. And that is why the Harold Haas, he told me that he was a mentor of the Philips and Osram companies, and they came to Harold Haas, sir, we will not do any business because the lights will not be bad. So how will do the business? People will not buy our earlier days. The tube gets defective, we go purchase, connect it, so their business was going on. So that time the Harold Haas told you enter into the communications. So people will buy your tubes. And that is the first time they have, and he made a big laboratory, he made a lot of experiments and big boss, and he would be able to push his ideas into the 5G communications. So this is, I have told, and this is the thing. Another important source of interference is the sunlight. That is the biggest source of interference. Even the other tungsten light source, like fluorescent lamps, if you did these fluorescent lamp lights in this room, when you do the LED communication, then those fluorescent lights will be interfered in that case. The green region is a visible light region. You see the sunlight has so much of spectral power density. It all contaminated your communications. And tungsten is a little bit. Sunlight is the most, and the fluorescent lamp. Fluorescent lamp and the sunlight are the most deterring factor about the noise in LED communications. So you see that before the photodiode, I put the ambient light, where the tungsten or from the sunlight it enters. So that part one has to take care of. So we have made a calculations here where the red curve, the red line, if you see, this line is a noise variance or the noise power of the sunlight. You see, it is such a huge effects on the LED communications. And the lower one, the pink one, is a thermal noise in the photo detector. And the green noise is the LED light is also having a noise, because this LED light is also consists of photons, So those photons, when impinge on the photodetector, it generates the short noise. The short noise power is still little below the sunlight contamination. So one has to be very, very careful to eliminate the sunlight contamination from the such kind of communications. So this is one important thing. And also not only that, if you want to increase the symbol rate, then it is a possibility that the interference symbols will occur. Means one symbol will overlap with another. Because symbol spreads gradually when you try to increase the symbol rate. Okay, so you see that interference symbol rate is also getting saturated. It doesn't allow you to increase the data rate. So one has to investigate the communication under such constraint of different noise sources. So let's come to the important topic of the white LEDs, the source of VLC communications. What is white LEDs? And there are two types of white LEDs. One is called the single chip and another is called trichromatic. The single chip was the earlier versions, which is basically, you see the phosphorus-based white LED generation. What it actually does, the blue LED, if you see the top figure, there is a blue LED chip. Okay, so there is a eminence of blue intensity. And when it goes to the phosphor layer, the phosphorence occurs and it spreads the wavelength. So it is basically acting as a wavelength converter. This phosphor is actually acting as a wavelength converter, which converts blue light emissions into a big range like this. This hump is created by the phosphor. So combining these two is actually a white light. But if you see, I will show you that such a light is slightly bluish tinge. It is not a pure white because the blue LED is actually the main source of light. But the second one, if you have a trichromatic LED, you have a red, green, and blue. Three LEDs are being put in there, and the three LEDs combinedly form a white light. As you know that a white light can be produced using R, G, and B color combinations. So using the three colors, R, G, and B, we can use the white, we can form the white light, which is much more pure white light. So if you see this diagram, this is an important diagram. If in the right side, you see that the left-hand side circle, which I show, is a bluish, is a blue luminance because of the phosphorus phenomenon. Okay, and if you use the trichromatic white LED, then you have a pure white, which is falling under the color temperature of the order of 6,000 Kelvin. So it is a very cool light, 6,000 Kelvin, the pure white color. So you can form this using the trichromatic LEDs. That is means using red, green, and blue. As I said, it could not be mounted earlier because of the green LED problem, because its efficiency went down, but we have solved this problem using the gallium nitride amplifiers nowadays. Okay, so let's go to the problem of the phosphor base. For communication, it's very difficult to use this phosphor based white LED to increase the data speed. Why? Because this phosphorence is a slow process. Because the phosphorence emission can last several milliseconds after the excitation is removed. Suppose you have a blue thing, you have a switch on and off. If you go off, still due to phosphorence, the emission will still go on. So that is why it slows down the switching response of the LEDs, and that is why we cannot go very high data rate using the phosphor-based white LED. But trichromatic LED doesn't have such kind of phosphorence phenomena. It can be used for very high-speed communications. So this is an important point. So when the white LEDs are available in the market, then this paper, the very beautiful paper, one can read this by Raja Gopal. He actually in IEEE magazine, communication magazine, he published this paper and he informed there that this IEEE 802.15.7, this white light communication has been standardized. So they understood that this white light will be a big source of communication. So immediately they standardize it and they give a name of IEEE 802.15.7. So what this standard says is, this standard says a lot of things that I will tell you. But along with that, they tell that other than the normal OK and on-off key modulations or the pulse width modulation, you should use the color shifting modulation. That is the future modulations. This paper has clearly stated that. But he could not state it the optical waveform because at that time waveform was not so prominent. But maybe nowadays it must be agreed with that. So this is what is the first modulation technique called the color shifting modulation for visible light communication using RGB LEDs. Because RGB LEDs, as I said, can give a high data rate, three trichromatic LEDs, and we can access. We did experiment with this RGB LED. You can have the access of R leads, D leads, and green leads. Everything is accessible to you. Okay, for sending the data. So this is the important point, that how this CSK actually works. For that, you need to understand that what is the meaning of chromaticity. What is chromaticity? Before that, we have the structure of our eye. Eye, you know that we have a cone cells and the red rod cells, you know, in our eye. Okay, so these cone cells are very much sensitive to color, and the rod cells are sensitive to entire visible spectrum. Okay, so but the sensation of color varies from person to person. The way I'm seeing the red, somebody else is seeing a different wavelength, the red, perceived at a different wavelength, this red line. So this is varying from person to person. So that is why International Commission of Illuminations, they standardize the measurement of color using some color matching functions and chromaticity of colors. They investigated in detail, experimented with different peoples, and they found out this is the color matching functions. You see the three color matching functions they have given. One is for the blue, one is for the green, and another is for the red. But they are overlapping. That is the noisy case, that they are overlapping. But this is the color matching functions they have given in the visible region. And using these color matching functions, what we can do, we can find out the X, Y, Z. This color matching function is X bar, Y bar, and Z bar multiplied by the LED powers. If you integrate it over the whole area under that curve, you can get the value of X. Similarly, you can get the value of Y, you can get the value of Z if you integrate each of the color or corresponding to that wavelength. So these X, Y, Z are called tri-stimulus value. And when these tri-stimulus values are being normalized, they called chromaticity. Okay, so the next slide is the chromaticity. You see that I have normalized this X with respect to X, Y, Z, small y with respect to that, and like that. So X, Y, Z are the chromaticity for the red, blue, and green color, like that. But the beauty is that the last equations, if you see that Z is equal to 1 minus X minus Y. That means if you know only X and Y, you can automatically interpolate Z using the last equations. So that is why the International Commission of Color, they give this standardization. In IEEE 802.15.7 standard speaks about this curve. This is the chromaticity curve. You see, there are red region, blue region, and green region. And in the periphery, you see the wavelengths they are given. This categorically said that you have to use this wavelength. You cannot use the other wavelength for this communication. Otherwise, inventory problem, a lot of other problems will come up. So they have specified this immediately in that standard, that these are the wavelengths can be used. So in our experiment, what we did, you can pick out any of the three wavelengths corresponding to one corresponding to blue, one corresponding to red, and another corresponding to green. Okay, so you see that I can make a triangle here where one wavelength I have taken from the green, another wavelength I have taken it from the blue, and another from the red region. So I have to make communication within this triangle. I can, if I increase the triangle area, it is better. So if I choose instead of 560, if I choose 510 in the green, then you see the size of the triangle becomes more. And why you will get the answer. So this is the same thing. So this is a triangle, and these are they have specified by 7 coordinate system. These are the wavelengths you have to use. 1 is the blue, 2 is the green, and 4 from the red region. So you have standardized it. And you see that is another triangle I have formed, as I told. Then comes, this is important because we ultimately have to increase the data rate. That is why we have to go for higher constellations. So like the normal communication, we have the 4 QPSK, 16 PSK like that. Similarly, simply CSK, if you go for 4 CSK, 8 CSK, and 16 CSK, you have to get the constellations. And this constellation can be easily done using some geometry. For example, in 4 CSK, if you just take out the meridian of the median between the 3 triangles, you get the common point is X2. Similarly, you can have some rules. You can find out the constellation positions in this way. So 8 CSK means 18 constellation, 8 constellation, 16 CSK means 16 constellation. So your beat has to be sent along with this constellation points using those wavelengths which I have just mentioned. That is very important. So you see that I am not going to detail. So some equations are there. You see X and Yn is the coordinates of any constellations, and XR, YR, XG, YG, which I make it in a red circle. Those are the coordinate points corresponding to 3 positions, blue, green, and 3 corners of the triangle. And X and Yn is any point, any constellation point inside this triangle. So if you know that which constellation you are going to transmit, you put the value in the x and y n, you know the other three, so you solve these three equations and find the values of L. And once you get the values of L, you can find out the LED power. So from that, how much of power you have to give to the LED that you can calculate using simple equations, solving these three equations. So this is what I've shown here. So I'm not narrating this. So this is how you can find out the power of the LEDs for transmissions. So this is what we did. So data is entering, scrambling, encoded, these common things. Now is the color coding. You see that color coding has been done, the CSK coding is being done. And then this XY chromaticity is being mapped into the LED, the three LED powers, PR, PG, and PV, the three LED powers, and that is being transmitted after the digital to analog. Everything is digital before D2A converter, and from there it becomes analog and transmitted through the LEDs. Okay. So far it's very simple, but the main problem is in the receiver. You should always remember that main problem, whatever you actually transmitted, main problem is the decoding. So you have to decode those constellations correctly. That is the challenge. That is why it is an open problem. I said decoding strategy of the CSK is still an open problem and is a challenging task. Why the challenging? You will understand. Many people have invented different strategy for decoding these constellations. We have proposed, this is our proposition, this is Radio Physics Electronics Department propositions, the Voronoi cell decoding. And I'm very fortunate that I got this idea from Dr. Vishal. He was a computational geometry, he worked. So he told me, why not use Voronoi segmentations? So I applied that, I got a beautiful results. So using this Voronoi segmentation algorithm, you see that I have made these lines, the blue lines between the two constellations. What is the algorithm says? The algorithm says that the line which you draw is always a midway between any two constellations. You see that blue lines x3 and x5, if you see that the line, horizontal line is between x3 and x4. If you see x5 and x7, that line is in middle. x9 and x5, you see the line is in the middle. So always using these rules, I can make these segmentations. Okay. So you see the whole chromaticity diagram, I made these segmentations. So that means if any incoming symbols falls inside any of the cell area, so that will be considered as x5. If it falls in the x5 cell. If it falls in x6 cells, any of the point within the false x6 cell, then it will be assumed that my x6 constellation has arrived. It is just like any other communications. But the cell splitting like this is a challenge. So we use the Voronoi segmentation algorithm for this. And this is for NCSK. We can use this Voronoi segmentation to decoding these constellations. Okay, so other people in Canada, Ontario, they have proposed this kind of segmentations called, they just put the disk. But the problem is that if you see that within the disk, there is some gap. So if it falls, if the incoming symbols falls in, so how to decide that in which constellation it belongs? So this is a very drawback of their constellations. So we compared this is a Voronoi flowchart. I'm just eliminating, I'm not telling this. So I just compared their symbol and a red versus SNR versus our results. Our result is a red line. You see this clearly, we have almost a 2 dB advantage from our Voronoi segmentations. Okay. So this is one paper also we have published in the journal. So what we have done in the IRP, I'll just very quickly go through because a lot of works, only I will state there only two works here. One, we have proposition and model here. You see that LED light is in the top and there is a photodiode at the corner of the room because that is the worst possible position is in a room. In a room in the center, it is the best position. But if you go at the corner, it's the worst position. So I put my detector at the worst positions and a lot of parameters are there which we have used for calculations of these symbols. I'm not going too deep. And also we have made the experiments also. And this is the experimental setup. And you see the input data, microcontroller for programming, for converting this chromaticity into the LED power. That calculation has been done there, and then the LED driver, it drives the LED, and then it transmitted. And then in the what we have done in the DSO, we have stored because we don't have the real time such a fast DSO. We have stored that thing, and then Voronoi segmentation algorithm is inside the MATLAB. So those data has been collected and seen that in which area Voronoi segmentation is actually followed. And accordingly, the symbols are decoded. Okay. So this is the offline. The last two states are the offline, but all other things are in the online, the real time. So experimentally, we have done these things. And we have got a lot of results. I'm not going to detail of this, but the most important thing is to say that the two equalization technique we have used. One is called the LMS, that is called least mean square algorithm, and this is called RLS, the roots linear square algorithm. And these two techniques, they are the equalization technique. And you see that when I do the equalizations, I have told in the very first slide that what ISI is the main culprit for increasing symbol rate. So if you do equalization, then ISI's problem is solved. Even at a high data rate, I can send the symbols, and you see all the things have been marked in the last curve here. You see all the equalized curves. So that means at much more lower SNI, you can work these communications. So we have done it, I think, in this case, 400 megabits per second, we are able to send the data. So this is one technique, the CSK route, and another work we have done using the optical OFDM. Optical OFDM, it offers the ISI-free communications, but the problem of the optical OFDM is, or any OFDM, is that it has a high peak to average power. The peak power suddenly shoot up, and that causes a problem because you have an amplifier. The peak power shoot up, the amplifier gets saturated, and it generates a lot of harmonics. And that is the biggest problem. And that one has to eliminate if one is to use the optical OFDM. So PAPR has to be removed. So if you see that this curve is the optical, I'm not narrating all the systems. It's the optical OFDM system, full thing is there. It is the signal which IF50 is done, then parallel to serial conversions, then some kind of clipping and modulation, etc., etc., etc. The laser being used at the end before the clipping. So you see these frequency subcarriers. When optical OFDM is, many subcarriers are being transmitted simultaneously. So those are the subcarriers I have shown, the N subcarriers. And when this, you don't know about the subcarriers. When one go high, one is low, because subcarriers sometimes can be combined coherently. And when they combine coherently, suddenly the power shoots up. You see this next slide, suddenly the power gets up. Because at that time, most of the subcarriers get coherently combined. So they shoots up, and that is why we call it high PAPR. We cannot allow this, because in the bottom part, you see that the amplifier is there. If we allow this, it will enter into the saturation power and it will generate harmonics. So we cannot allow this. So we have to clip this. And once you clip this, that is the biggest problem. You see, I have clipped this thing. I have to clip, otherwise it will generate harmonics. But if you clip this, this is the problem. You see that the constellation positions of 16 CSK, the plus red are the ideal positions. And when due to clipping, you see the constellation have been defocusing because of the clipping, okay? And if you increase the clipping by 8 dB, 6 dB like that, if you do that, the start of the spectrum, the middle one, has been also raising. So that is actually, it is deteriorating the whole system. So like that, so OFDM clipping noise is the biggest problem. So that one has to eliminate. That is the biggest challenge of. So this is a paper which this is basically a state-of-the-art paper, and it has been in ICC. They have presented it in, and what they have did, instead of, if you have many carriers, there's a probability that it can combine suddenly. But if you have a very few carriers, the chances of having combined is less. So what they have did, of the 16 carriers, they have made it 4, 4, 4, 4 in a group. The first 4 being sent to one LED, second 4 sent to another LED like this. So they have split it up, and all being transmitted by the LED there. So in this way, they have reduced the chances of high peak to average power and made this. Another technique they have done, they have made it like this: one carrier in the first one, the second one is from the second. You see that is interlacing. The top one only after 4 it has been there. It continuously 4 first one, and the second one you see after 4 it has been sent. In between, you have another one from second one, another one from third one, another one from fourth. So it is basically interlaced. If you in this way also, you can have a less PAPR. So, what we have proposed, this thing. We have proposed, don't do this anything. But we will send the OFDM at a time, but we will do some kind of pre-coding. You see, there's a block here. If you see in the middle after constellation mapping, you have put a block here called pre-coder. So this pre-coder block actually has a less chance to have a simultaneous that the peak occurs coherently. So this pre-coding algorithm we have developed, and this is using a very simple fly, as we have read in our communications and the BTEC class, the roots raised cosine functions that we have used. So root raised cosine and the raised cosine pulses being used to generate a pre-coding matrix. And that pre-coding matrix is multiplied Yes, if you go before, I just multiplied with the carrier, and this is basically a pre-coding carriers being transmitted. Because of this pre-coding, you see that I have shown that without pre-coding, you see the PAPR is so high. But when you use the pre-coding, immediately the peak average power has come down. So this pre-coding works beautifully. And when we compared this complementary cumulative distribution function, in all the communication, we have to show this complementary cumulative distribution function, where I've shown that the chances of this PAPR greater than PAPR threshold. PAPR 0 means PAPR threshold. Chances of higher PAPR over the threshold, that it tells with the threshold. So you see that our proposed curve is that blue curve. Blue curve is the PAPR proposed curve, and you see that it works beautifully at a much reduced symbol rate, okay, at 10 to the power minus 4. So it actually reduces of getting high PAPR of 10 to the power minus 4 probability, okay. So it's definitely, it works better compared to the earlier ones. And this is beautiful results we have also got in the simulation, that without pre-coding, you see the symbols are quite desired in the left side. And when we use pre-coding, immediately the constellations are rightly focused on the actual positions. So that means the PAPR is actually working, and it is able to bring the constellation point at its right positions. So that's all. I think I will not go beyond, because within short time it's very difficult to explain all the mathematical part. I just give you an overview. And other than this, we have also did a lot of work, LED linearization technique, ILA, that means indirect learning architecture, that is also been published. So we give an overview. We showed you how light LEDs are being modulated using CSA, color shifting modulations. CSK demodulation techniques using Gormy algorithm I have showed. In optical waveframe, I have shown a glimpse, and how to mitigate the PAPR is a challenge to optical waveframe I have also shown using decoding techniques. So some of the publications we have made in PLC like this, and we have some references, important references, and thanks acknowledged to my own PhD and MPhil students. Okay, I hope I'm in time. You see? Yeah.
Actually, we are not only living like 1 year, 1.5 years. So, I shall no, it's not Philips. Philips not Philips. Yeah.
Actually, it is not made by Philips. Actually, all they given a lot of NSA, they have opened up. Those Philips, they get stamped, authorized by the Philips, and get stamped.
High cost. Still.
Yeah, but at least
we are 2 years.
no, but in my house, I have seen it almost 2.5 years.
2 years.
Right, but you guys actually put this one money yet. And obviously, 7 months.
But how the legs can be repaired?
That is the problem. That is the problem.
This is a real
In the chain, when I go, I see that lot of LED bulbs they are selling with a very low cost. Setup.
Yes.
Because those are all the repairing. After throw out, they again make it low.
Now I'd like to request
Okay.
PKB sir to present ADB sir with a payment target button of that.
I'm really glad because that is my supervisor and we are accepting this. Thank you.